Hi, and welcome to Module 2 of Lecture 11. In the previous module, we discussed vector spaces generally, and if that was a little too general for you, just keep in mind that vector spaces are just collections or sets of vectors that have some common properties. For instance, here's R3, the Euclidean space, three-dimensional space. You can write vectors like this that have some common length, 3. You can add these, subtract these, multiply these by scalars, take dot products because they're the same length, and so on. And they have lengths, norms, and all those properties together, plus the vectors themselves, form a vector space. That's it, just a collection of vectors with some common properties. Okay. So now we're going to move from that general description of vector spaces to some more specific properties of vector spaces that can come in useful. The first is going to be a linear combination. Now, a linear combination is a combination of vectors that's linear. To see what that means, we can think back to linear functions, right? If a function is linear, then we know we can do two things. One, we can add elements, and two, we can multiply each thing by constants. So this looks like a linear function. Well, a linear combination is the same thing. Let's choose some constant t and choose some vector x, which can represent a point in space. And let's take 1 minus t and then have a different point in space, y, different vector. Well, this thing is a linear combination. It's a linear combination of x and y. And it represents, geometrically, the line joining x and y, or the whole line that contains x and y in it. Why is that? Well, if t equals 1, then at t equals 1, this just gives you x, right? At t equals 0, it just gives you y. And for other values at t, it gives you things that are along the line joining x. So if this is x, and this is y, then this thing, and I'm not going to draw the line correctly, but let's look at the line, is a line joining x and y. That's a linear combination. We can do the exact same thing for 3 vectors, 3 points, but instead of getting a line, and this is backwards from the book, doesn't make a difference, you get a plane. This is the plane containing these 3 points. In other words, having 3 points, and assuming they're not in the same line, can represent a plane, and this is a plane drawn from those 3 points. You can go bigger things there if you choose. So you know in each case, here there are 2 dimensions of these vectors, and the combination gives you a 1-dimensional line. Here there are 3 points, and the combination gives you a plane. So it's 1 fewer dimension in dimensions of the vectors themselves and the number of vectors. You can keep going with this. If you have 4 vectors that are 4-dimensional, you can make a combination to get a 3-dimensional object. We call all these things hyperplanes. A hyperplane is just a plane of 1 fewer dimension, a space of 1 fewer dimension than the overall space you're dealing with. So here a line has 1 fewer dimension than a plane. Here a plane has 1 fewer dimension than 3-dimensional space. A 3-dimensional hyperplane has 1 fewer dimension than a 4-dimensional space, and so on. You see this rarely, but you do see this sometimes in proofs that come up in social choice theory when trying to figure out how spaces of preferences operate. So if you see that term there, you know what it means now. It just means a space 1 smaller than the space in which it's embedded in, of 1 fewer dimension than the space it's embedded in. So that's a hyperplane. And these things are just geometric objects. We can create normal vectors to them. So if, for instance, the vectors x and p are in some plane, and want to figure out what's perpendicular to that plane, we can recall that the dot product, if the dot product is 0, then 2 vectors are perpendicular. So here's 1 vector, here's another vector. If that equals 0, then and x and p are in the plane, then n is a normal vector to that plane. And this doesn't just mean planes, this can be anything. So if we have a vector here that's x minus y, then the normal vector, which would be perpendicular to this thing, would be a vector such that the dot product with this is 0. So, and this would be normal and therefore perpendicular. So there you go with some geometric interpretations. You might be thinking now, okay, well, this doesn't seem very relevant to a lot of stuff. Fair enough. But linear combinations, besides being pretty common, are a necessary precursor to the concept of linear independence. So it's linear independence. So what's linear independence? Well, it says that a linear combination of vectors has all the vectors independent of each other. Okay, that's clear as mud. So what does that mean exactly? First, let's start off with a linear combination. So let's make a pretty general one. Here's a1, x1, plus a2, x2. The a's are all constants, the x's are all vectors, and we can keep going through n of these things. A combination of vectors is the set of vectors is linearly independent if whenever I'll just call it C for the moment, make my life easier. Whenever C equals 0, A1 equals A2 equals dot 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 dot, sweet dots, AN equals 0. In other words, the only way to get a 0 vector out of this combination is if all the coefficients on the vectors are 0. Why is that? Well, let's say that was not true. Let's say you could get 0 some other way. Well, then you'd have a1 x1 plus a2 x2 plus blah 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 an xn equals to 0 without the a's being 0. So I could choose one of the a's that's not 0 and move that one to the other side. So let's say a1 is not 0. Then I can move x1 to the other side, and I get that, and that's going to be equal to negative a2 x2, well, moving all of them to the side, I guess, an xn, and then x1 is this exact combination of the other vectors. In other words, the vectors are not independent. I can get one of them from a linear combination of another one, of the other ones. So another way of saying this is that a set of vectors is linearly independent if I cannot obtain any other vectors from a linear combination of the remaining vectors. So if I cannot choose a single vector and then get that vector with a linear combination of other vectors. So in practice, let's see how that works. Let's do nice two-dimensional ones for the moment. So let's say I have this vector and this vector. Are they independent? Well, can I get the first one by some combination of the second one? Well, no, because there's only one vector here to combine, so it's pretty simple. And there's no number, no constant I can multiply by this to get that. Right? So they're linearly independent. So they're a more complicated example. Well, let's show an example where they're not independent. If instead I had this, well, then I can multiply the second vector by a half, and that vector would give me the first vector, because a half times 2, 4 equals 1, 2. So these vectors are not independent, and therefore we cannot treat them as independent. And this will have implications we'll talk about in a moment. Okay, how about a little higher dimensional stuff? Let's do 1, 2, 3, because it's easy to write, remember. And let's say I have another vector, 3, 6, not that 2, 8, and then 0, 1, 1. 3 vectors. Are they independent? Well, they're independent if there's no combination of any two that that can be written to make the third one. Now, at this point, you might be wondering, whoa, this seems actually kind of difficult, right? How do I just know this by looking at it? Because if I look at this equation right here, these 3 vectors right here, rather, okay, it's clear that no multiple of any one of them directly forms a different one, but it's less clear that no possible combination of 2 forms a third one because I can do things to combinations, right? I can subtract, I can multiply, 5 times the third one, and then subtract it from the second one, see what happens there, and so on. So there's things I can do. We'll get to a simpler way to figure out if this is independent or not by the end of this module. But it's independent if there's no linear combination of these vectors, of two of the vectors that can create the third one. Or rather, if it's independent if the third one cannot be written as a linear combination of the other two. So that's linear independence. There's a bunch of things we're going to do with linear independence, one of which goes to the notion of spanning vectors. Okay, so we'll get back to showing how that works in a second, but let's move on for the moment to spanning vectors. A bunch of vectors, a collection of vectors, span some space if you can write any vector in that space as a linear combination of the spanning vectors. You've seen examples before all the time. So in two-dimensional space, we can write the vectors E, which is 1, 0, and E2, so E1 and E2, which is 0, 1. I can write any vector in two-dimensional space by a combination of those two things. Why? Well, here's a random vector, Z. Well, Z could be A, E1 plus B, E2. This is a linear combination of those two vectors. Well, that's going to equal A times 0 plus 0 times B, which is going to 0B rather, not A times 0, sorry, A comma 0 plus 0 comma B. Then A plus 0 is 0, 0 plus B is B, so you get this. Since AB is, for some A and B, is any vector in the space, I have now spanned this space using these two vectors. If I add a third one, I would get 0, 0, 1, and there'd be zeros at the end of these things. I can have a three-dimensional basis space. Rather, a basis for three-dimensional, for three-dimensional space. So, what's the point of this? A couple of things. One, it lets you write other vectors in terms of these core vectors. And two, it lets you understand the dimension of the space. The dimension of a space is the smallest number of linearly independent vectors that span the space. That tells you the dimension of the space. What's that? Well, for two-dimensional space, you can't write a two-dimensional vector with fewer than two vectors, two spanning vectors, so the space is two-dimensional. How do we see that involving linear independence? Well, if you have the vector 1, 0, we can call them now. These should actually be column vectors in theory. I think most of these are just defaulted column vectors. Here's the transpose. I'm just writing, it's just easier to write this on the tablet here. So we have two-dimensional space, 0, 1, 0, and 0, 1. Well, note there's no possible way you can no number you can multiply this one by this one to get the first one, right? The only number that gets you the first one is 0, right? So 0 times this vector would give you 0, 0, but that would get you the first one on top. So there's no way of multiplying any constant times either of these two vectors and getting the other one. So the two vectors are linearly independent. Now, we said smallest number. Can we add more vectors? Well, we could. We could add this vector. And this vector this vector is not independent. So we can add that vector, but we don't need it because we can write that 3, 2 by 3 times the first vector plus 2 times the second vector. Now, they all span the space, so if I had these three vectors together, they would also span the space because I could write any two-dimensional vector as a combination of those three vectors, right? For instance, I could write 6, 4 as 2 times the third one. It would save me some time. But it's not the minimal set. It's not a minimal set of linearly independent vectors. And that's sort of the minimal set you need to span a space. Now, why do you care about that? there's a couple reasons you care about that, but you largely care about that to understand the dimension of the space. The dimension of a space is different from the number of the dimension of the vector itself. For instance, let's take the space spanned by 0, 0 and 0, 1, 0 only, just those two vectors. Well, this is what's typically referred to as the x-axis and the y-axis. Even though we're in three-dimensional space, these two vectors by themselves allow you to form any vector in a plane, a flat plane at z equals 0, a horizontal plane. Those two vectors that you span a horizontal plane only, so the dimension of the space spanned by those vectors is 2, not 3. Each individual vector is 3 elements, so each individual vector is three-dimensional, but the space spanned by the vectors is only 2. We're going to see the utility of this most often when we deal with solving equations, which we're going to do in the next module. We'll discuss how this relates to equation solving. But this is also useful in general for understanding the space you're actually dealing with. For these two examples, it's easy, comparatively easy, but it's less easy when you have, say, let's see, what am I doing here? 4, 8, no, 3, 12, yeah. And let's do, so this is a relatively easy one because I can do it on the tablet quickly. But it looks like there are 4 vectors here. Each one is three-dimensional. So is the space three-dimensional? Because you have more than enough vectors, in theory. But if you look at them, they're all dependent on each other. In fact, you can get the second by multiplying 2 times the first. The third is 2 times the second. And the fourth is 2 times the third. So actually, there's only one vector here that's independent. Any one will work. But this first one could be independent. Right, there's only one independent vector here. The others are dependent on that one. Should note, it doesn't matter which one you choose to be independent. You can always get the other ones by multiplying by 2 or by a half. Doesn't matter, right? So a half times the second one is the first one, or 2 times the first is the second. Doesn't make a difference. Point is, there's only one independent vector here, which means, despite the fact you have 4 vectors, each of which is 3 dimensions, the dimension of the space spanned by these vectors is 1. So if you were to draw a graph here, you have a point at 3, 1, 2, right? I can't do the 3 dimensions here well enough, but you have a point at 3, 1, 2, and the line, the vector from 0 to that point defines a one-dimensional space. It's a line from 0 through that point, right? Back and forth. It's a one-dimensional space only. It is not, in fact, 4-dimensional. And you'll see more complicated examples like this, in which even though you might think naively that the space is equal to the number of dimensions, the dimensions of the space is equal to the number of dimensions of the vectors, it's not, because they're independent, because they're dependent in some fashion. They don't form a unique space. This has most relevance moving back to this equation solving and matrices. But one last point before I get to that. Note from all these examples, you don't need 0, 1, 1, 0, whatever to span a space. For instance, 1, 1 and 1, negative 1 also span 2-dimensional space. They are linearly independent. They span the space. You can write anything you want by either adding or subtracting combinations of these things. To see that, if you just add them, you get 2, 0. If you subtract, you get 0, 2. And then you can get whatever you want from those numbers. And you can see this graphically. So for instance, these two vectors span the space, but so do these two, and so do these two, and so on. Any two vectors that are linearly independent span the space. So there you go. And now going back to what I said before, which is how do we use these practically? Well, this goes back to the thing we put aside earlier, which is how do we go about trying to figure out if a set of vectors is linearly independent? Well, you could go through and try to figure out if there's any possible combination by hand, but an easy way of doing it is to write all the vectors in a matrix. So here's x1, 1, x1, 2. I'll do this way actually. x2, 1, x3, 1. So we're going to put them all in rows this time because it fits with our earlier notation. So here's three-dimensional vector 1. Here's three-dimensional vector 2 in this row. It doesn't matter if you do row or column. And here's three-dimensional vector 3 in this row. So we just stacked each of the 3 row vectors on top of each other. Now why do we do that? Well, this relates to a concept of matrices we have not talked about yet, called the matrix rank. The matrix rank is the number of linearly independent rows or linearly independent columns. These numbers will always be the same for all matrices. The matrix rank is relevant because it helps tell us if the matrix is, if it's a square matrix, if the matrix is singular or not. If the matrix rank, which again is the number of linearly independent rows or columns, is equal to the total number of rows or columns, in other words, if all the rows or all the columns are independent of each other, are linearly independent, then the matrix has a full rank. We say rank equal to the number of dimensions of the matrix. A matrix with full rank is non-singular. A non-singular matrix, recall, can be inverted and has a non-zero determinant. So a really straightforward way of determining if a set of vectors is linearly independent or not is to stack them either in columns or in rows into a matrix. You get a square matrix then, because assuming you have the same number of rows or columns, assuming you have the same number of vectors as dimensions of each vector, you get a square matrix. So if it's three-dimensional, if each vector is three-dimensional, then you need 3 vectors. You stack them into a matrix, and when you do that, you take the determinant. If the determinant is 0, the vectors are linearly dependent. If the determinant is non-zero, the vectors are linearly independent. That's a nice, convenient way to do that for reasonably sized vectors, because we've already gone through and learned how to actually compute determinants. And frankly, even for big vectors, you can use this technique using some kind of computer aid, because computer aids have determinants built into them. Matrix programs like R have determinants built into them, like MATLAB and things, and you can just go through and compute the determinant. If it's 0, the vectors are dependent, and if it's non-zero, the vectors are independent. Note that you don't have to worry about different numbers of vectors. So if you have 4 vectors in R3, you know that one of them is dependent, right? Because R3 is a 3-dimensional space. No space can be spanned. No space has a basis, and a basis, again, if it makes it clear, a basis is the minimal number of linearly independent vectors that span it. Now, R3 has a basis of 3. In general, a space, an n-dimensional space, will have a basis that is n big, have n vectors in that basis. If you have 4 vectors, they can't all, in that 3-dimensional space, they can't all be independent. Right? In other words, one of those 4 vectors has to have been a combination of the other 3, because you know in a 3-dimensional space, the minimum basis for anything we're going to deal with is going to be, right, x, y, z. There's 3 dimensions. You can get anything from there you want. So a 4th vector can't be part of that basis. In other words, you can convert the existing 3 whatever 3 vectors you have, if they're independent, you can convert them into that basis right here, and then the 4th vector will necessarily be dependent on the other 3. Similarly, if you have a 3-dimensional space but 2 vectors, then you can't possibly span the space, as we saw with that plain example. Any 2 vectors will create at most a plane. So therefore, you can't span the whole space of two vectors, and therefore the rank of a matrix you form from here is not going to be full. So you can't have, so this would be if you put them in rows, this would be a 4x3 matrix. That would not be full rank. It would most be three-dimensional. The rank would most be 3, not 4. Down here, you would have 2 rows and 3 columns, and again, the rank would be 2 instead of 3. So for non-square matrices, the point is you don't have to worry about that so much. But for a square matrix, again, if the determinant is 0, the matrix is singular, and that means that the matrix itself has less than full rank, which means that at least one of the rows or the columns can be written as a linear combination of the other ones. So the vectors are linearly dependent. If the determinant is non-zero, the matrix is non-singular, and the rows or columns are linearly independent. The rows and columns are linearly independent. The matrix has full rank. Okay. That was a bunch, and it might seem confusing now. You might have to go back a couple of times here. This is the most conceptual one of the modules in this particular lecture. But really, we're looking at a couple. So I'm going to go back really quick and go over the topics again because it's worthwhile, I think, to do so. We have linear combinations, which are just ways of writing different vectors as other vectors. We have the concept of linear independence, which was saying that there's no way of writing any of a set of vectors as a linear combination of the other ones. We have the concept of spanning. A set of vectors spans a space if you can write any vector in that space as a linear combination of these spanning vectors. We have the notion of a basis, which is the sort of minimal number of linear independent vectors that span the space. Note, bases are not unique. 0, this one over here is a basis of a two-dimensional space, right? So is this one, and so on. So you can get anything you want from these things. So that's basis. Now, span basis, what else would you rank. I mean, matrix rank is the smallest number, is the number of linearly independent rows or columns in a matrix. Matrix here. And this connects to linear independence and so on. So there you go. That's the LV. That's not LV. So that's what we've done so far. There's the concepts. Work through. You have to look at this. Read the. Sorry, if you have to watch this again, do so. But work through that. There's some examples in the problem sets of spanning vectors and bases and linear independent and so on. But the main notion of all this stuff is to understand the dimension of the space you're working in, because the dimension will tell you things like how many solutions are present in the system of equations. And that's important to know for a bunch of stuff, and we'll talk about that in the next module. Before we go on, though, one last thing is the notion of quadratic forms. This is not strictly linear algebra anymore. Quadratic forms, because we're no longer being linear, but it's the exact same technology we've built up so far, so it's worth just sticking in here real fast. If x is a vector, then this is a quadratic form. Here's A as a matrix. X transpose AX is a quadratic form. Note that if X is a column vector, then X transpose is a row vector. If A is square, right, and the square matrix times the column vector gives you a column vector. The row vector times the column vector is basically a dot product, so it gives you a scalar. So this thing here is a scalar, and this is going to be a quadratic form. If this thing, the reason we care about this is if this thing ends up being greater than 0 for all values of x, we say the matrix A is positive definite. This can come up a lot when we work on optimization. Well, not a lot, but it can come up when we do optimization in more than one dimension. At the last part of this class, if it's less than 0, it's negative definite. And if it's greater than or equal to, or less than or equal to, it's positive or negative semi-definite. again, file this away somewhere. This will come up in the last part of the class a bunch when we're trying to understand how to figure out if something is a minimum or maximum in more than one dimension. Okay, so that's the end of this one. And again, there's a bunch here. There's a relative lot of sort of conceptual ideas, but it boils down to understanding how to construct spaces, like everyday spaces, the kind you can visualize in your head in 3 dimensions or 2 dimensions and so on, out of vectors, and how we know if the vectors are needed to form a space, what's the minimum number, and what's the dimension of the space. How big is the space we actually have here? Because, well, we'll get to that next, and we'll get to the major use of this in the next module, looking at the notion of solution sets. Thank you very much.